Welcome, everybody. It is my pleasure. I'm going to get us started so we have plenty of time because we're just at coming up at 5 at the hour. You have come to this talk probably because have heard a little bit about CASH or know of us, and we'll put our link into the chat for those of you who don't. Everybody here is encouraged to join our newsletter or to make use of all the coding resources that we are making available. We also have a pilot project call for submission for seed grants coming up, so check out those. We'll put those links in the chat so everybody has them. So those are, I'm joined by Lori Hunter, the co-director of CASH with me, but Lori is, I think, on the phone for this particular talk or in and out in the mountains. So I'm gonna move on and introduce our speakers. For those of you who were with us 2 weeks ago, approximately 2.5 weeks ago, we had Kris Karnauskas, and again, Julia Shipman will put in the chat a link and everybody can watch his fantastic talk. I'll introduce Kris again in a second because he's going to help moderate this, but our main speaker today is Christian Braneon, and Dr. Braneon is an affiliate of the CUNY, City University of New York, where I am, the Institute for Demographic Research. He's an award-winning climate scientist that serves on the New York City panel on climate change, as well as the board of directors for the Tract of Governors Island. He also serves as a research physical scientist at NASA's Goddard Institute for Space Studies, also called GISS, where he leads the urban pillar of its impacts group. Dr. Braneon previously served on the leadership team at Carbon Direct, and as the director of climate justice and as co-director of the US EPA's inaugural Environmental Justice Academy for Community Leaders. He was selected as one of 4 international recipients of the AXA Award for Climate Science in 2021 for his contributions to understanding climate change and related adaptation strategies. So Christian will be our main speaker, and our moderator I'm going to introduce is Kris Karnauskas, who gave our talk last time. I recommend everybody to watch it. It's 45 minutes of really fun climate introduction, and we have a video of it. Kris is a fellow of the Cooperative Institute for Research on Environmental Science and associate professor in the Department of Atmospheric and Oceanic Sciences at the University of Colorado Boulder, and with secondary faculty appointments at CU's School of Medicine and Colorado's School of Public Health. Professor Karnauskas currently serves as editor-in-chief of the Geophysical Research Letters and co-chairs the joint U.S. CLIVAR NIH Working Group on Climate and Health, and recently served as on the Scientific Steering Committee of the U.S. Climate Variability and Predictions Program. So with that, Kris, I'm going to pass it to you to give the rules of the engagement for today's seminar, and then Christian can take it away with the talk itself. Thanks, everyone, for coming.
Okay, thanks, Deborah. Yep, so Christian is the real speaker today. I am just here to help moderate the questions and I have a nice discussion at the end. So if you have a question that you want to ask during the talk, we want to encourage you to please do that. Just raise your hand. If Christian doesn't notice that because he can't see it or whatever on his screen with his slides, I might be the one to interrupt him, but we can go ahead and ask questions along the way. Christian said that was okay. But if you have a question that you don't really want to interrupt the flow of the talk, then just drop it in the chat. I'm going to keep an eye on that, and we'll be sure to come back to you towards the end. So, yep, with that, Christian, please take it away.
All right. Thank you so much for that introduction, Dr. Balk, and thank you, Dr. Karnauskas, for helping out with moderating. I'm going to share my screen now, and we'll get going. Can you guys see my screen?
Yep.
Awesome. Good. All right. Well, first, I'm going to talk about climate variability and try to unpack that for you before transitioning into a discussion of climate risk. What is it? How do we characterize it? How are folks thinking about it? And then I'm going to dig into developing projections for interdisciplinary research and also give you some examples. And then we should have some time for discussion and Q&A at the end, but feel free to ask questions as we go along. So let's start with climate variability. Weather is really describing what you experience on any given day or any given week or any given month or year. And when we describe climate, it's distinct from weather because we're really considering long-term patterns of observed weather. And so typically the gold standard is to consider 30 years of data and develop statistics associated with that 30 years of data to describe climate. You'll sometimes see folks use shorter time periods depending on the goals for their research, the goals of their study, the available data that they're using along with those weather observations or those climate model outputs. But weather and climate are distinct. And so I want to start by clarifying that. In any given year, most days are going to be average temperature. You're going to have some days you think of as a little cool or a little hot. Some days are definitively hot or definitively cool. But typically, you're not going to have a lot of days that folks would consider very hot or very cold based on what you would typically experience in a given location on Earth. And so this collection of cool and hot days and average days create a distribution around temperature. And with global warming, with climate change, we expect that distribution to shift. And we expect that distribution to shift to the right. And so we expect there'll be many more very hot days. The way the distribution can shift, if you look over to the right at that top figure, it could shift in a way that is associated with a shift in the mean of that distribution. And that's certainly what we expect in the future. But we also expect an increase in the variance around that distribution. So we actually expect that there's going to be more extreme heat events, more days where folks would consider the temperature really hot or very hot. And what we're observing right now is actually an increase in the mean and the variance. So we're actually seeing a shift, not just in the central tendency of that distribution or kind of the mean of that distribution, but also in the variance. So we're seeing hot weather, hot temperatures that we've never seen before, and folks expect that over time, decades into the future, but we're already seeing some of this in the present, that there'll be more heat-related deaths, there'll be more heat-related hospitalizations as a result of this. And so, one way to think of one way that we're observing this. Oh, go ahead. Yeah.
Sorry for the rude interruption, but there's on your Zoom screen, it says the Zoom app, blah, blah, blah. There's a little thing that says hide. Yeah, just move that off because we can't read the x-axis. Yeah, great. Thank you.
Sure. Yeah, thanks for that. Thanks for that. Yeah, I was hoping you guys couldn't see that, but you could. So we're actually seeing this in real time when we look at the temperatures we're observing on land. And the way we typically think about temperature in the context of climate science, we're gonna typically compare an historical period to a future period. And so if we compare land temperatures historically with what we're observing in recent times, we see a shift in the distribution of land temperatures. And that shift coincides with that previous slide I showed. So we're seeing a shift in the mean to the right. We're seeing temperatures, in recent decades to be, over 2 degrees Fahrenheit or so higher over land. But we're also seeing the distribution spread out and the tails of the distribution grow, particularly on the right. And so this kind of perfectly coincides with that figure I showed previously. And we're seeing really in recent years record-breaking temperatures on the surface of the Earth. If we think about air temperature, right on the surface, less than 7 or 8 feet above where you could stand on Earth. We're seeing record-breaking temperatures. 2024 was extremely hot. 2023 was also hot. And even though any given year really varies in terms of what you might observe in terms of temperature, there's a lot of variability from year to year. We've really seen an uptick in terms of extreme heat in recent years. One way to think about this is that, if you compared, 1850 to 1900, this time period where the Industrial Revolution is just taking shape, you start to see the increase in global temperatures kind of pick up early in the 20th century. And as we've approached late 20th century and now the 21st century, we've really seen an acceleration in warming. And I'm showing you these values in Fahrenheit specifically because I know this audience is a US-based audience, even though you're going to often see results presented in degrees Celsius. But in recent years, any questions or any doubt about global warming have been resolved. In the early 90s, folks really didn't have enough information or enough observations in some cases to really thoroughly describe what we might what is happening in terms of climate change. But since the 90s, particularly over the last 30 years or so, we're seeing just such a strong increase in global warming that it's alarming, and folks are more motivated to take action. What I just showed you is averaging temperatures across the whole Earth, but we're seeing similar trends at the local scale. So this is observed data from New York City. We can see an increase in annual temperature at 3 different weather observations in New York, shown here. We're seeing increases in the minimum temperature you might see every day, or the maximum temperature you might see. This is data associated with aggregated across an entire year. And you're also seeing precipitation increase in some areas. You might expect to see that. We don't have as strong a signal, or we're not as confident about what we might see in the future in terms of precipitation as what we might see in terms of temperature. But in places like New York, we are seeing increased rainfall. You expect that air is able to hold more moisture in a warming climate. Where that rain will fall is not always, it's not obvious. There's a lot that we still need to learn about cloud physics, but we are seeing increased rainfall, and with increased rainfall, we'd expect to also see extreme increases in extreme rainfall events. So with that, I want to transition and talk to you about components of climate risk. Before I go there, any questions that I should address, Kris?
Nope, Christian, it's looking good. Yep.
Okay, good. So risk is a function of the likelihood of an event and the consequences associated with that event happening. And by bringing the likelihood of the event and the consequences together, we can quantify the risk. And this becomes the basic building block for risk assessment and risk management. These events that we're concerned with in the context of climate change, could be droughts, they could be floods, they could be severe weather. Any event that we're concerned with that's tied to weather would fit as an extreme weather event. And over time, different industries, different fields have used simple as well as approaches to characterizing risk. On the simpler end, you can develop a matrix with the likelihood of different impacts and think about the severity of impacts. And even though you might focus in some cases on the most likely impacts, you can't rule out and you can't ignore impacts that are less likely that have really severe consequences. And these sometimes are described as tail risks. But over time, as the climate science field has grown, we've come to characterize risk as having these components. We've come to characterize risk as being associated with hazards, exposures, and vulnerability. Hazards being the probability of an occurrence of an extreme weather event. Exposure has to do with the people and the assets that are exposed, and vulnerability really has to do with the propensity for people or assets to be impacted. And in some cases, you'll see vulnerability broken down into sensitivity of people or assets. So for people, you might think that folks are more sensitive if they're under 4 years old, for example, or over 65 years old. and also the adaptive capacity of people or assets. Does a person have air conditioning? Does a system have resiliency options installed, or resiliency options that can be implemented? And sometimes you'll see exposure and vulnerability linked more closely than this. But for this talk, I'm going to focus on hazard and exposure and vulnerability as the key components, which I think you're gonna always see come up in research and in practice. And so hazards, exposure, and vulnerability come together to form climate risk conceptually. And we can reduce greenhouse gas emissions as a way to reduce the likelihood of hazards. And we can adapt and become more resilient as a way to address exposure and vulnerability. And so in this way, we can think of climate risk as a function of hazards, exposure, and vulnerability. With this framing, you can characterize the current climate risk, and you can imagine that climate risk is dynamic and that it evolves over time, and that if we don't address greenhouse gas emissions, that hazard likelihood grows. And that's what you see on the right, where you see this second scenario in the future. And you can imagine risk grows. Even if exposure and vulnerability stay the same, there is no change, the risk would grow because the likelihood of the hazard grows. But then you could also imagine a scenario in the future where the likelihood of the hazard grows, but the vulnerability of people and assets is reduced because we took some adaptation measures. And you could even imagine that the exposure to those people and those assets is reduced. And yet the risk still may grow because the likelihood of the hazard grows over time. And so if we try to approach assessing risk, one approach that's a useful starting point is to characterize the risk, in the current climate or under some baseline period, and then imagine how that risk evolves in the future. And one way to do this is to characterize the risk components themselves. You have to make some assumptions in this case. You have to assume that there's some stationarity as a result, some temporal stationarity as it relates to how exposure, vulnerability, and hazards are defined. But assuming so, you could determine how risk is amplified over time as a result of climate change. And folks will often, use a ratio so that a percentage change is described. So you might say to yourself, if there's this many deaths in the current climate, maybe there's going to be 20% more deaths in the future, for example. But sometimes folks will also just try to come up with a quantitative number. So if there were 5 deaths in a given location associated with extreme heat in the current climate, you might say, oh, there could be 10 deaths in the future. So these are kind of common ways to characterize risk, to think about risk, but there's other ways that folks can approach it. What's becoming increasingly important is to also consider how adaptation influences climate risk. And so folks are beginning to weave that into their studies, to weave that into their research. What if in a location where folks that are vulnerable, what if folks take measures to get more air conditioning access? How is that accounted for as we address climate risk? And that's represented in part in this figure. And so, even if we do try to become more resilient in the future, even if we do take measures to adapt to climate change, there's going to be some hard limits to adaptation, and there's just limits around human health, right? There's just temperatures that are just too high for folks to survive. You might have air conditioning on inside your home or inside a building where folks work, but they're going to have to walk outside at some point, right? And so we can imagine that there's some limits, and an important area of research is to kind of try to understand those limits and what can we do in terms of adaptation, and what is just really beyond interventions. All right. So with that, I want to transition and talk a little bit about how folks are applying climate projections for interdisciplinary research, and also give you a few examples. Let me stop again, Kris. This is kind of the meat of the presentation, but I wanted to see any questions I should address.
Yeah, nothing's been posted, but please,
Okay.
if you have one right now, go right ahead and unmute yourself and ask.
Okay.
I'm going to ask one and maybe others will join in. This is Deborah. So, in the propeller diagram that you were showing, which I know it's used by IPCC and other assessment bodies. Can you talk a little bit about how much is known about the contributions of those? This is a schematic and it's very helpful, but empirically, like whether the hazard is growing or the exposure is growing or the vulnerability is growing, and whether can you comment on our ability to measure these various spokes of this propeller? Maybe you're getting to this anyway, but if you're
Yeah, it's a great question. Yeah, I'll get to some of it. I would say that we we really can do a pretty good job describing how hazards associated with extreme heat are growing with time. You're going to see folks um, not just explain like how hazards related to extreme heat change regionally, but you're also seeing folks now describe how it happens at the local level, in a given city, in a given town. I think the vulnerability is more challenging to address because you'll find some confounding information, right? And I'll talk a little bit about this, but for example, um, in New York State, what folks have found is that um, there's a big leap, there's a big jump when you consider folks age 25 and above as it relates to hospitalizations associated with extreme heat. There's a big jump if you're over 25 versus under 25, and then you don't really see that big jump happen again, at age 44 or age 65, and that might be intuitively what you would expect. And what folks realize is what it has to do with the fact that folks 25 to 44 are more likely to be working outside, um, and they're just exposed differently than folks that are under 25 or over 65. And that's going to be different in any state or any county in the United States or any part of the world. So vulnerability is challenging to address. We don't know what folks are going to do in the future in terms of adaptation. We don't necessarily know perfectly where folks are going to live, and so we don't know necessarily what the exposure will be in that sense, or what their daily routine is going to be. But that's where social scientists come in, folks that are demographers like yourself, Dr. Balk, and others, to help us understand where are people moving, how is their lifestyle changing. So I would say, the piece of the puzzle that I'm most focused on is the likelihood of the hazard, the frequency, the duration, the intensity of extreme weather events. And we have a fairly good handle on that in terms of temperature. We're less certain in terms of precipitation, and we're less certain in terms of things that events that happen that um, uh, could be derived from understanding of temperature and precipitation. But we have some confidence around what's going to happen in the future. Sea level rise, though, as a hazard, is quite uncertain because of deep uncertainty, because of known unknowns and unknown unknowns. And so more confidence about temperature-related hazards, less confidence about precipitation-related hazards. And just to give you an example, in terms of sea level rise is an interesting hazard because there's so many known unknowns and unknown unknowns around ice sheet dynamics, which will strongly contribute to future rises in sea level. Hope that answers your question.
Yes, thanks. It promotes another one, but I will save it for later.
Okay. So let's talk about a few examples that I can share, and just I want to share a few insights on developing projections. We use global climate models to develop projections of future climate. These are complex computer models that use greenhouse gas emissions as an input. And the way we do this is that, smart people imagine scenarios in the future where technology evolves and there's changes in economies around the world, and there's shifts in population, and by assuming some plausible future that we would call a scenario, we can imagine how greenhouse gas emissions will evolve, and then that becomes an input into our global climate models. These global climate models are really representing the entire Earth, and they work by linking the atmosphere and the oceans and allowing interactions between land and the atmosphere and land and the oceans. They're really simulating exchanges of momentum and water vapor and energy using differential equations, and they're run with supercomputers. And there's a limitation because of the massive scale in that the outputs of these global climate models will come to us on a grid that's typically hundreds of kilometers in scale. And so there's a limitation there. And so we have a better understanding of what may happen in regions around the world than any specific location, but we can downscale the outputs from global climate models using observed data to better understand what might happen in a given city or a given town, or what may happen at the local scale. But anyway, they're extremely useful because we can simulate future climate. We can also simulate historical conditions with climate models. And in that way, what we'll often do is simulate historical conditions, simulate future conditions, and then we can look at the differences to understand what may be coming in the future. I want to say something about these greenhouse gas emission scenarios. The big thing I'll share about this is that we can't really ascribe likelihood to what may happen in terms of greenhouse gas emissions in the future. We don't know what's going to happen in terms of technology and international cooperation and really just global action around greenhouse gas emissions. So we've come up with scenarios, and over time, depending on advances in science and changes in policy, folks may feel that one emission scenario is more likely than the other. And so a good practice is to present your results for multiple emission scenarios, or to at least use multiple emission scenarios as you characterize your results. But what I'm showing you here on the figure on the left are different global warming levels, and you can see, and this is for certain global warming levels by 2050. And what you can see is on the low end, SSP1 1.9 only achieves about only represents about 3,000 gigatons of CO2 emitted since 2050, and that's associated with a warming level that could be bracketed at kind of around 1.5 degrees Celsius. And in a higher end emission scenario, we're imagining upwards of 4,000 gigatons of CO2 is emitted since 1850, and then you expect then that global warming levels will exceed 2 degrees Celsius, right, by 2050. So there's a huge range in here, but right now you're often going to see folks use the scenarios associated with SSP1, SSP2, SSP3, SSP5. We don't typically see folks thinking of SSP1 as a realistic a future, based on our trajectory. But this evolves over time, and it really is going to depend on the actions we take. Now, if you take the outputs from a collection of global climate models, you can then create kind of a conditional probability that's associated with different environmental outputs of interest. And it's conditional on those models you chose, right? It's not a true way to think about the likelihood of an event. Those models are forced by emission scenarios, as I stated. So it's implicitly conditional on the emission scenario you chose. It's implicitly conditional on the climate models you chose. But with those assumptions, with those constraints that you set yourself, you can then derive a distribution of model outcomes. And you can derive a low estimate and a high estimate, with the low estimate being associated with lower emissions. if you use multiple emission scenarios, and a higher estimate associated with higher emissions if you use a higher emission scenario. And so your distribution could look something like this. These are some results, estimating how the frequency of extreme weather events will change in New York City. And in red, you can see the distribution you get with 13 models versus 16 models. These results are using 2 different emission scenarios, and a moderate emission scenario and a high emission scenario. And you see there's a difference in the distribution, when you use 13 models versus 16 models, but not such a huge difference. But if I showed you result for just 1 model versus 16 models, it'd be drastically different. And that's why a best practice is to use as many global climate models as you can. Upwards of a dozen makes a lot of sense, I think, in many cases. Although you can still produce compelling results with just a handful of global climate models, but I would not suggest presenting results for just 1 global climate model, because there's so much model variability between the different models and the outcomes you might see. Another example I'll show you is some work done in Belize, where historically in that 1981 to 2005 time period, you might have observed about 110 degrees Fahrenheit as the maximum temperature you might see. And that's, roughly using global climate models. When we look historically, that would be about 45.5 degrees Celsius. That would be about the hottest day you might have observed in Belize in the past. When you use a moderate emission scenario and a high emission scenario, by the 2020s, you're expecting about 8 of those days, and on the low end, and maybe 9 on the high end. And by the 2050s, so this grows quite a bit, to the point that the high estimate, really gets scary, really gets frightening. And we're starting to see some of this unfold already in the 2020s. And then, you can also, instead of using downscaled information and really focusing on the local scale, there's some really interesting studies that can be done where you look globally. And what I'm showing you here is the increase in really dangerous heat where the heat index is greater than 103 degrees Fahrenheit. This heat index being a function of temperature and humidity, essentially, are a function of temperature and the amount of water vapor in the air. And what you see is this tremendous growth and this steady growth in the number of days each year that are dangerous for folks outside, agricultural laborers outside, but all kinds of folks are outside, of course. And you really see this concentration in a number of really dangerous days in places near the equator. But it's not perfectly distributed around the equator, right? You're seeing really hot days manifest themselves in places that aren't right on the equator. Whether places are going to be super hot is moderated by the cloud cover and the amount of vegetation and the tendency for the environment to be urbanized. And so it's going to vary depending where you are around the world, but consistently research is showing that there's going to be more really hot days. And this is just an example of how folks are using climate models to understand this. But climate models are just one piece of the puzzle. Emission scenarios are just one piece of the puzzle. This figure is really kind of explaining that, even looking at something like heat, which becomes the low-hanging fruit when folks do climate change research around health, because we have more confidence in terms of what we expect in terms of temperature than precipitation or sea level rise. Even when you consider heat health outcomes in a warming climate, there's other things to consider. We talked about adaptation, but we also need to think about populations and how populations shift and change. We need to account for natural climate variability, which one way to do this is to derive those statistics over decades. But also the bioclimate models we use, our understanding and our models of how the body responds to different stressors, that's going to evolve, and we need to address the uncertainty in those models, right? So there's really quite a bit of different quite a few different contributors to uncertainty. And it may be difficult in your work to address all of these, but you need to be aware of them and include these caveats in your work when you don't address any of these types of uncertainty. A really interesting study, and a study that's really informed a lot of my work, is some work done in New York State, where researchers actually collected hospitalization information for 5 years and also collected near surface air temperature data from the National Land Data Simulation System. And they were able to characterize the likelihood of hospitalization as temperatures increase on very hot days. And what I want to point you to is that they used the NLDOS data set. This is a reanalysis data set that combines modeled outputs with observations from satellites and other data inputs. And this is pretty coarse in resolution. This is a study focused on historical data. It's not super fine in resolution. It's on the order of 12 kilometers by 12 kilometers in spatial scale. But they actually compared, they did their work, they compared the results using kind of the sparse network of weather observations in New York State. Everywhere around the U.S. and in pretty much around the world, there's not really a lot of there's not really dense weather station networks, and so folks are tending to in the past at least base their results on the proximity to a weather station and kind of make some assumptions about how weather changes as you move away from that weather station, because as soon as you're not sitting right on top of that weather station, the temperature is going to be slightly different, the precipitation is going to be a little bit different. But with the NLDOS data set, because of the spatial scale of the study, they're doing with often National Weather Service advisory messages coming out at the county scale. 12 kilometers by 12 kilometers is kind of appropriate, right, for the work that they were doing. And so they were able to kind of derive relationships between exposure to heat at the state level, and they were able to derive really interesting risk ratios and kind of derive this for not just temperature, but also the maximum heat index observed. They looked at heat stress, acute kidney failure, dehydration, and cardiovascular disease. And in the blue, I'm showing you, the blue dot represents, the first onset of hospitalizations that was observed in the historical data. And then in the red, you're seeing where the risk ratio reaches 1, where you're really starting to observe that consistent uptick in morbidity or in hospitalizations. And so by characterizing this, they were able to help local leaders and the National Weather Service rethink when they issued heat advisories, right? And there's some tension here because heat advisories in the United States are issued at the county scale. A county may be associated with one town or city, but it might be associated with multiple towns and cities. You can imagine this is a large area, right? And some parts of a town or city may be hotter than others. Some places may have more trees, more green space. Other areas may have more built materials, and so radiation is absorbed by those built materials and radiated all the time. And this creates an urban heat island effect such that some parts of a given town or city are potentially hotter than others, and there's other factors too that may influence why one part of a town or city is hotter than another. And so you have to be really careful about when you issue these heat advisory warnings. But with this information, folks decided that 100, using a heat index of 100 degrees was probably not appropriate, and they actually shifted to 95 degrees. And so this is a really, this is not part of their paper. This is just, I'm showing you this red line that depicts that shift just so you're aware of how they were able to influence the National Weather Service's actions. And so, this work came out, or this work was happening, and as a result of this work, there was a change made to the threshold that's used to issue heat advisories. And now that it's been some time since this work came out, I don't have the exact what I'm showing you on the right. Is what was effective June 2018. But what would be interesting to do in future work is to revisit this, and see, does it make sense to potentially revise this again? Also see, did this actually ultimately reduce, morbidity? Did this change actually reduce hospitalizations? Another study I want to share with you is focused on Europe. And, in this study, they're trying to understand net changes in temperature-related excess deaths. So, there's cold weather in Europe, but there's also hot weather. A lot of folks don't have air conditioning in Europe. And there's been this question of whether heat-related deaths are much more relevant than cold-related deaths in the future. You would imagine under a warming climate, you may have less cold extremes, less cold-related deaths. And in their study, they actually look at 3 scenarios in the future: SSP 1.2.6, SSP 4.5, SSP 7.0. And they try to understand, are you seeing more or less deaths associated with cold weather versus hot weather in the future? Also, what is the net effect, right? If you see a decrease in cold deaths, how is that balanced out by an increase in hot deaths? They look at adaptation and how this influences deaths, as well as the no adaptation scenario. I'm just showing you the no adaptation scenario. So this work is really novel in that they did consider adaptation. And they also allowed for their environmental response functions, kind of their functions associated with deaths and temperature. They allowed that uncertainty to be characterized using Monte Carlo simulations. So they actually perturb their models, many times to try to characterize that uncertainty. But anyway, what I want to point to is that with the 19 global climate models they used, and this kind of coincides with work I showed earlier, you can see that there's different timing for when you reach 1.5 degrees Celsius of warming versus 2 degrees Celsius versus 3 degrees Celsius versus 4. And for that lower end emission scenario, you never quite reach 3 degrees or 4 degrees Celsius, right? So if you use that lower end emission scenario, the deaths only climb so much in terms of extreme heat. Using a higher end emission scenario, you can reach as high as 4 degrees Celsius, and the darkness in this gray bar is associated with 5-year increments of time. And so which each 5-year increment is corresponding to is when that global climate model, I should say the concentration, the number of global climate models that reach that level of warming in that 5-year window. And so most models under SSP 7.0 are reaching 1.5 degrees C, around just after 2025, 2 degrees C around 2050, and so forth. And as you might expect, as you start to use a higher emission scenario, you see more deaths associated with extreme heat, but you see less deaths associated with cold. And what that tells you is that distribution is shifting to the right? The central tendency is shifting, but also the tails are shifting. And that tail, if you have a distribution associated with deaths and temperature, that tail associated with cold weather on the left is changing as well. So this is a really interesting study that I wanted to point you to. And they're using some of the best practices I mentioned. They're using 19 global climate models. They're showing results from multiple emission scenarios. They're trying to quantify the uncertainty associated with the models they use to describe the response of between temperature and death. And so, these are great best practices that I want to point to. This is at the city scale, and so they use that NASA's next GDP data set, the NASA Earth Exchange global downscale data set. And that data set is at a finer resolution than the outputs that come from the global climate models, which is great. And so they're basically using outputs, they're using grids that lie over those cities to get these results. They would not be able to represent something like this if they used those coarser outputs. You would not see the variability you would see without using a downscale data set. So that's what I wanted to share with you today. I hope that stimulates some discussion. I think we have about 10 minutes left, and I'm going to stop sharing my screen and let's.
So Christian, I'm going to let Kris navigate your Q&A for you. But before we do that, I think Julia is going to put in the chat a quick survey that we're going to ask people to go ahead and to take, and you can get a and while Julia does this, puts the survey link in the chat and people take a moment to answer it, Kris can start teeing up the questions for you to answer. And other people are encouraged to also come off mute and ask questions as well as they wish. So great, there's one coming in the chat too. So so thanks. Okay, Kris, to you.
Yeah, thanks, Christian. That was an amazing talk, wide-ranging, and there's quite a few questions here. I'm gonna go up to Luann Thompson, Professor Thompson from the University of Washington, asked a really big question that has kind of spawned into a couple other questions. So let me hold on to that one for a second. And there's perhaps a quicker one by Salen, who asked, when you were talking about the heat advisory in the Northeast, Salen asked whether the heat advisory threshold accounts for age or other demographic groups, given that the effects of heat might be different for different populations.
Yeah, that's a great question. That really speaks to why the heat advisory was adjusted. But my understanding is that they're thinking about hospitalizations and deaths as they come up with that heat advisory, and they're not necessarily directly addressing whether some populations are older in some counties versus other counties. And so the work that I showed has really probed the National Weather Service and folks in the Northeast to say, we need to treat each county differently, right? And some counties may have an aging population versus a population that's not aging the same way. They may have different migration patterns. But my understanding is that it's really focused on, the health outcomes themselves in an aggregate way, not necessarily, keenly focused on the demographics.
Let's knock out another one that might be quicker. Perhaps it's one that you might want to drop something in the chat in response, but
Okay.
Oops. Yashan Wang asked which study or what website does the figure on dangerous hot days for agriculture workers come from?
Yeah. I'll so that's from NASA's Scientific Visualization Studio, and so I'll drop a link to that in the chat. That is one of my favorite visualizations to show, so I'm glad you like it. So I'll drop a link to that in the chat.
Great. And again, if you have a question you want to just interactively chime in here, just go ahead and raise your hand. We'll call on you right away. But there was a really interesting, fact dropped by Professor Thompson that I think has spawned a couple of directions we could go, Christian. Luann mentioned that it's becoming clear that when it rains harder. And Luann said that can probably partially explain the huge amount of rain in Hurricane Helene last year. That inspired a thought by Deborah. Deborah, why don't you just go ahead and do that? It raised a question in my mind too when it comes to climate models, but let's go in the social sciences direction here. with Deborah. You want to unmute?
Sure, I'm happy to. And Luana's free to come off mute and also contribute to the conversation. That would be great. So well, the question that occurs to me, it brings up these issues of the spatial and temporal scales. So like the idea that you have like these huge rain events in part that happens, like when we have rain, the rain comes much harder. So the volume of it is much greater. And, Christian, you did show that one, like that graph that had like the heat and rain on it, or the temperature and rain on it, and they were a precip. But I wonder in the spokes that we have in the propeller diagram, I don't know that the spatial and temporal scales are compatible and that we paid enough attention to their compatibility. So that's the comment that I put in here. Like, I think like some of the vulnerability like builds over a life course, and some of the exposures could do that too, but some of them might be really instantaneous, as in the case of the immense amount of either wind or rain that we get from these events. So, and like these increasing storms. So I'm going to just leave it there with feel free to comment on as much of it, or like what's on the next hurrah on the science of all this. And I also invite Luann to chime in if she wants.
Yeah, yeah. And thank you. I just want to thank you for that question, Deborah. And Julia, I just want to say thank you for adding the survey to the chat again. Folks, this is a really quick survey that's really important for our virtual centers work. So just take a moment, just take you less than a minute to fill that out. Yeah, so because of this huge spatial scale that global climate models operate at Dr. Balk, which is hundreds of kilometers. This is so much larger than the scale of a cloud, right? Like a cloud you see in the sky. And so we're attempting to take what we can observe and relate that to the physics of clouds and global climate models, but it's just so disparate, right? And so we're increasingly seeing a behavior around rainfall that we can't really describe that well, because there's just a mismatch between the spatial scale of our observations around rainfall, we're able to understand about clouds, and a scale that global climate models operate. I think folks are trying new machine learning approaches and other techniques to better resolve the physics that we haven't been able to address. But the other piece to your question is that exposure is not necessarily just instantaneous over the course of a day or a month. It could be over the course of years. And so really a really important area of research moving forward is using cumulative exposure, right? And doing that in more thoughtful and creative ways. So imagine studies where you use agent-based modeling and you actually try to imagine how much time someone spent outside versus inside, and even modeled what temperatures might look like inside versus outside. And that's really important because we see lags in when folks are hospitalized and when they die, around the time of extreme events. So basically aligning the scale of observations or modeled outputs with the time scale, but also the spatial scale around the exposure is, I think, a growing area of research. And I think there's really much more work to do there, although it's been challenging to date. So I hope that answers your question. I think it's really a big topic, a big question that you're getting at. And what folks are trying to do is have folks wear sensors sometimes, for example, to understand their exposure better, having folks put sensors in their homes. But this is really difficult work for folks to do.
Well, being mindful of your time, Christian, and everybody else who's on this call, we're kind of in our final couple minutes here. Is there one last question that someone would like to ask? I think we've covered most of what's in the chat.
Yeah, and I was able to drop that link to the visualization in the chat. Thank you, and Cozy Muse.
Yeah, thanks. There are other comments here. That's great. Yeah, thanks, Cozy.
He's just noting that folks do pay attention to sensitive groups. And folks, I just want to flag again, don't forget to do that survey. Take you less than a minute. Helps us have the resources to do more seminars like this.
Maybe people aren't watching the chat, but I did stick a question about SSPs with both the SSP RCP framework came up in the last talk with Kris and again today. And maybe if people would be interested in seeing an SSP, unpacking those SSPs, the RCP SSP framework, we'd love to hear from you if this is something you would like to hear another, unpacking what those are. It gets pretty technical. It's pretty interesting. We see them frequently, so would love to hear more. We'd like to know how much interest there is in that, and we could organize something around that as well.
Technical, yes, but not too technical to show up in the recent executive order, actually. So
exactly.
what timing? But I'm guessing Christian doesn't want to unpack that in the last 30 seconds here. So we should probably wrap it up, Deborah. I'll kick it to you or Julia but from my perspective, Christian, that was an amazing talk, just as a fellow scientist. Thank you. I learned a lot. Deborah?
No, thank you, Kris, for monitoring this, and Christian for it was a fantastic talk. Really appreciated it. There are a bunch of links in the chat for anybody who wants them, and there will be a recording so that we can share this with our friends. And come on back when we have our next one. We will have something for junior scholars coming in the fall, early in the fall. All comers are welcome, including ideas about more that you'd like to hear about. So come back to us and let us know, and we'll take it under advisement. So thanks, Christian and Kris, and everybody who joined us today. Bye.